Thank you. Thanks so much for the introduction. Very casual, and thanks for the invite to give this tutorial. So I wanted to give a tutorial on something in combinatorics because it's sort of been a very prominent part of reverse math, and I'll say more in just a second. But somehow that would connect to some more modern things, so that I'm not just talking about kind of classical things or old things. So that's the idea here, and I'll explain more in a second. Before I do, I just want to say I'll put copies of all these slides on my website, so you can find them there if you want to look back at anything. And then also, of course, my email is there, so feel free to get in touch if you have any questions. I know some of you, not all of you, so it's also nice to meet new people this way. So please feel free to get in touch. Okay, so as I said, combinatorics has had a very important role in the development and the kind of drive of reverse mathematics through most of its history. And what I want to do then is to survey some of the important kind of techniques and ideas and themes used in computable combinatorics or reverse mathematics of combinatorics, but to do it through a sort of more recent lens. And so, in fact, that lens is sort of computable topology in this sort of weak sense that I'll be talking about here. And in particular, what I'll do is I'll focus the entire talk around this somewhat recent paper that I wrote with Heidi, Benham, Andrew, DeLapo, Reed, Solomon, Java, Darlene, Villano. And then Heidi, Andrew, and Java are actually here. So if I mess anything up, you can talk to them, and they can also keep me honest on anything I say wrong. So anything that doesn't have a citation in these slides will always be a result from this paper, right? What's interesting, and I find very surprising, is that this paper is about a theorem, and so this is a reverse mathematics paper, and it analyzes in the way that we do a theorem in topology that on its face has nothing at all to do with combinatorics, but in fact it turns out to be sort of deeply connected to combinatorics and require going back in a nice way to some of these classical techniques that I'd like to survey and to push them a little further, in some cases quite a bit further. So this is the idea behind the title of this talk, right? From topology to combinatorics. So we'll use this theorem as our kind of conduit for doing that. And at the same time, it also allows us to look at how is at least one particular way of developing formalizing topology in second-order arithmetic. Okay, but as this is the first talk on reverse mathematics proper, I'll also give some background. So some of that might be very familiar to certainly some of you. Maybe for some it will be a useful review, okay? Okay, so let's begin. So this is the theorem. This is the theorem that is a lovely theorem that almost nobody has ever heard of, but it's a delightful theorem. It's by Ginsburg Sands, 1979. It says the following: suppose you have an infinite topological space, then it always has a subspace which is homeomorphic to the natural numbers with one of the following 5 topologies on it. It could be the indiscrete topology, so the only open sets are the empty set and omega. It could be the initial segment topology. So the open sets are, okay, there's always these, right? But then you have these half-open, these initial intervals. It could be the final segment or co-initial segment topology, right? Where you have the complements of those intervals, the intervals n to infinity. It could be the discrete topology, so everything's open. Or it could be the cofinite topology. So the non-trivial open sets are exactly the cofinite subsets of the natural. Okay, so you always have, in any infinite topological space, you always have a subspace like this, homeomorphic to one of these. That's a very nice kind of regularity property, right? And of course, if you know some combinatorics, it should be somewhat reminiscent of these kinds of theorems that say, well, in any kind of object of, any kind of complexity, whatever, there's some order inherent in it in some case, right? So of course, it does remind us of that. And one way to think of it is as this is one of these kinds of properties, as a homogeneity property. So I'll talk a lot more about Ramsey's theorem soon, and in particular tomorrow. But let's just look at a very simple form. This is just the infinitary pigeonhole principle, right? So one way to state that is to say that if you have a coloring of omega with, let's say, two colors, red and blue, then there's an infinite subset of omega, which is monochromatic for one of those two colors. Okay, so this is a property that one can think of as being somehow analogous to what the Ginsburg Sands theorem on the previous slide was telling us, right? So what are some of the similarities? So, okay, you can't be a homogeneous set that's both blue and red, right? You can only be one. And similarly, if you are homeomorphic to one of those five subspaces, you can only be homeomorphic to one of them. You can't be homeomorphic to two. So you can't be discrete and indiscrete or indiscrete. And this is a property that is closed under infinite subset. So if you're an infinite subset of a red homogeneous set, you're red homogeneous. If you're an infinite subspace of a discrete subspace, you are, under the subspace topology, going to be a discrete subspace. Right? So these properties are also inherited under the relevant subobject. And so in that sense, it's a homogeneity property or a minimality property. This is what Ginsburg and Sands called it in their paper. They thought of it as a minimality theorem for topological spaces. Right? These are the minimal, in their view, these were the minimal topological spaces. Okay. All right. So this is the theorem that in this paper that I mentioned at the beginning, this five-way paper we analyzed. We were interested in the strength of this theorem. And let me begin by giving you just the proof of this theorem, right? The Ginsburg Sands theorem. It has a lovely proof, and this is the original classical proof from 1979. So it's absolutely beautiful. So let's fix an infinite topological space, and let's just go ahead and assume it's countable. We can always take a countable subspace. And now let's do the following to begin with. Let's define an equivalence relation on X by saying 2 points in the space are equivalent if they're in each other's closure, pointwise closure. So X in the closure of Y means that every open set containing X also contains Y. Okay? So 2 points are equivalent if you can't separate them at all by open sets, right? Any open set containing one contains the other. Okay, so let's do some cases. If there's an infinite equivalence class, right, then that's one big open set that contains all the points in that equivalence class, and they can't be separated further. So that is, under the subspace topology, homeomorphic to the indiscrete topology. That's one case. Okay, so now suppose there's not this doesn't happen, right? There's no infinite equivalence class. So then every equivalence class is finite. Means we can pick representatives out of each equivalence class, right? And just to think of drop anything in any one of these finite equivalents. So we can just think we only have the representatives of the equivalence classes. So that means our space is T0. That means for any two pairs of points, distinct points, you can find an open set containing one and not the other. You might not be able to do it in both directions, though. It's not necessarily a T1 space, right? But it's T0. Okay. And now we can define a partial order, and you can check if you want that it is in fact a partial order. We're going to say X is less than Y if X is in the closure of Y. Now it really is a partial order as opposed to a quasi-order because X and Y cannot both be in each other's closure. Okay. So now we have some combinatorial things coming in, right? So we have this partial order up there again, and we can apply this very nice result, it's a sort of variant of Dilworth's theorem, that says that if you have an infinite partial order, then it either has an infinite chain, everything's comparable, or an infinite antichain, nothing is comparable. Right? Okay, so again, let's consider the two cases separately. First, let's think we have an infinite chain. So that's a linear order, right? That's a linear order under this partial order. Okay, then we have two further subcases. So if you have an infinite linear order, it's just a nice result, right? And we'll talk about these results shortly more. But if you have an infinite linear order, it either has an ascending sequence, so something of order type omega, right? So everything has finitely many predecessors, or it has a descending sequence, so something of type omega star. So every element has only finitely many successors. Okay. Well, now you can sort of check, right? Remember what the definition of this is with respect to the closure, that if you have an ascending sequence, that's exactly corresponds to a final segment, a subspace with the final segment topology. Whereas if you have a descending sequence, then that exactly corresponds to the initial segment. Okay, so maybe reversed from what you might think at first, but just think about how the implication goes, right, with respect to the definition. Okay. So that leaves one case. That's the case where when we apply this principle here, we are left with an anti-chain. Again, we have this definition, and now we assume there's no infinite anti-chain. So let's just assume the set itself, for simplicity, is an anti-chain under this relation. Right? So no two elements are in each other's closure. That's exactly to say that the space is T1. Right? That's what the separation axiom is. Okay, so now what are the cases? We've already covered the indiscrete, the final segment, and the initial segment. Right? And the other two possibilities from the Ginsburg Sands theorem were discrete or cofinite topology. Right? Okay, so a couple of remarks. First, let's just assume that it has no infinite subspace with the cofinite topology. And let's build now a subspace with the discrete topology on it. Okay, so we'll use that assumption that it has no infinite subspace homeomorphic to the omega with the cofinite topology. Okay, so first of all, in a T1 space, points are closed. Right? You have to think back to your point set topology days, but you can easily do that. And therefore, the cofinite subsets are always open. All the cofinite subsets are open. So what does that mean? That means, okay, that means that every if you have an infinite subset of our space, there has to be, so all the cofinite subsets are open, so it cannot be that there is a subspace whose open sets are only the cofinite subset, right? Otherwise, we would have a contradiction to this assumption that there is no subspace with the cofinite topology. So with this, what our assumption means is that if you give me an infinite subset, any infinite subset of our space X, there has to be an infinite open set U which intersects that set and whose complement inside that set is still infinite, right? So there has to be an open set which in the subset is both infinite and co-infinite. Otherwise, we'd be done. Okay, so we're going to use that fact now to construct, recursively construct a discrete subspace, right? So what are we going to do? We're going to define this subspace Y. We're going to call the elements x0, x1. And along the way, we're going to build these witnessing open sets U0, U1. What U0 will do is it'll contain x0, but not any of the others. U1 will contain x1, but not any of the others, right? And that in the subspace topology will witness that this is a discrete subspace. Is that okay? Everybody with me? Okay, so how do we do that? So I will draw a picture, right? So here's X. This is X, right? It's an infinite set. So by the assumption that we had, there's an open set whose complement is infinite. It's non-empty and whose complement is infinite. Okay, so there it is. There's an infinite set, an infinite open set. There's a point inside it, and this space, this region here is still infinite. Okay, so we pick some point in here, and that's our x0, right? And we let this open set be u0. And the idea is now we're going to pick the rest of all the points in this complement. Okay, now what do? We apply the assumption to this region, to this infinite subspace here, right? Again, there has to be an open set which intersects this region and whose complement in that region is still infinite, right? Now that open set might go into the previous region that we did, right? Because the open sets come from the parent space. Maybe even contains this point, but points are closed, so we can delete them. So what's our next point? Well, we pick a point here in the space. That's our x1. And our witnessing set then is just going to be this open set minus that point. Right? And we keep going. And this now produces the desired subspace. Right? So that's an incredibly beautiful proof. And you can see right off bat why we were interested in it, right? Because it's a topological theorem, but there's some heavy uses of some, at least to people who have seen some computable combinatorics, some well-known combinatorial principles, right? So we've used the existence of chains or anti-chains in partial orders and the existence of ascending, descending sequences in linear orders, both of which are well-known consequences of Ramsey's theorem for pairs. Right? So this is already there's something kind of tantalizing because that's what reverse mathematics at the end of the day kind of likes to address, right? When you use something in reverse mathematics, some principle is used, the the question is, why are we using it? Why did we use this principle? Did we have to use it? Was that the right thing to use, and so on? Right? Okay, so that's the kind of the motivation for studying. Oh, sorry. Here's one more. One more point. Okay, good. There's a lot of work to make these pictures, so I really feel bad that I didn't use it. Okay. All right. So let's recap this construction. So there's sort of three main components here, right? The first one was the definition of this equivalence class using the point closure operator. And then in the case where there was no infinite equivalence class, this partial order, right? Both defined in terms of the closure. The second was the application of these combinatorial facts about partial and linear orders that I've already talked about. And then the third step was some kind of inductive construction to handle the T1 case. That's when so those were the three kind of moments in the proof, right? All right, and so what do we want to know? We want to know this thing that I've already spoken about. Is this somehow, are these the optimal proof? Is this necessary? Why, is this natural to somehow use these things? What can we say, right? Is the use of combinatorics necessary? And as we'll see, actually, we can answer this quite convincingly for this theorem, right? We can really answer these questions very nicely. Okay. Any questions about that before I move on? All right, so let me give a little informal, like your introduction, little sort of casual introduction to reverse mathematics, right? So very brief, right? So what are we doing in reverse mathematics, at least in this kind of classical reverse mathematics? We're going to use second order arithmetic. So what's the language of second order arithmetic? Well, we have this usual kind of signature of arithmetic, plus we have an epsilon relation, and we have a two-sorted, still first order, but two-sorted theory, two sorts of variables, right? First sort, second sort, or first order, second order. We have these variables that sort of are intended to range over numbers. We have these variables that are intended to range over sets. This thing can only relate first sort and second sort terms. This can only relate first sort terms, right? So equality in particular is not, we're not taking equality to be a primitive between sets, right, or set variables. Yeah, in particular, we have the x equals y for sets means what it should mean, right? And then we can define the usual syntactic classes. And when we're dealing with models, which I'll talk about in a second, we can also use parameters, right? Which you can think of in the formulas. They are treated as like universal closures with free variables, free set variables floating around. Okay. Sorry, I think I'm doing that. All right. What's actual second order arithmetic as a theory now? So we have these kind of usual algebraic axioms of the natural numbers, right? So all these examples. 0 is the additive identity, and then basic facts defining relating addition and the successor, and everything has a least successor, and all these things, right? All the basic things you can think. We also have a comprehension scheme, which allows us to form sets, right? Sets of numbers. So if you give me any formula phi in this free variable here, then there's an axiom that says there is a set x, a second order variable, such that the elements of it are exactly the things satisfying that formula. And we have induction, right? So if you have a formula phi, then we have the usual statement of induction, right? If phi holds of 0, and whenever it holds of x, it also holds of x plus 1, then it holds for all x. You have full induction, full comprehension and of course, this is a very strong theory. At least I know there was some set theorists here earlier and in the room, so this is very weak for you, but for me, this is very strong, right? Z2 is a powerful theory. So we want to break it down a little bit. So we're going to look at fragments of it, and these have been called subsystems of second order. Right? So I want to highlight two which will be relevant for my tutorial. The first one, of course, is RCA 0. I don't know if Kate is going to talk about, or maybe Anton is going to talk about something weaker than RCA 0, but okay, good. All right, so good. This is a good starting point. So we're going to use this as our base theory then. Okay, so what's RCA0? So it has the algebraic axioms, PA minus. It's going to have induction restricted just to sigma 1 formulas, right? That's what the 0 there stands for. And it has comprehension restricted to, delta 1 formulas, right? So formulas, sigma 1 formulas phi, which are provably equivalent to some pi 1 formula of psi. Yeah. So for those kinds of formulas, we can form the sets defined by those formulas. Okay? So RCA stands for recursive comprehension axiom, right? And this is a good theory, a nice kind of formal analog of computable mathematics. So what can we do in RCA not? We can do things using primitive recursion. We can use the minimization operator. So we can build things by standard kind of recursive procedures. The only kind of issue is that, when in the real world, as it were, you're doing some kind of argument and you're saying, well, and now take the least thing with this or something, this thing exists, so take the least thing, right? Those are potential issues here, right? Because we have, when you say least something or first something, those are really questions about induction. And our induction here is very limited, right? We only have sigma 1 induction. So in principle, you have to take some care when you're formalizing kind of, let's say, a recursive definition or something like that in RCA not, that you can actually do it with sigma 1 induction. We'll have some examples later on just to show where that kind of need for care arises and how you actually implement it. We can also, in RCA not, prove lots of good things about kind of that standard algebraic manipulations of the numbers and so on are possible, right? We have this pairing function. We can prove things about codings, all kinds of, we can code finite sets as numbers and things like that. This is all good. And then I'll just say this about notation, right? We use this blackboard n as opposed to omega when we're talking about things in RCA not, because in an arbitrary model of RCA not, of course, n might not be omega, right? It might be a non-standard version of the natural numbers. So I'll try to, which is to say I've already written the slides, so maybe I've made mistakes, but I have tried to use this when I'm talking sort of syntactically or trying to write something formally, and omega when I'm talking in the real world. Okay, so that's RCA not. That's one system. That's going to be the weakest system I ever touch. Here's ACA not. This will be the strongest system we're going to talk about today in this tutorial. ACA not is RCA not plus comprehension for sigma 1 formulas. Right, so now anything you can define by any sigma 1 form, doesn't have to be provably equivalent to a pi 1 formula. Any sigma 1 formula you can form the set defined by that. And in fact, right, this is much more powerful because ACA not in fact proves comprehension for, just from sigma 1 comprehension you can get sigma 2 comprehension, sigma 3 comprehension, all full arithmetical comprehension. Right? So here's an example, right? Suppose you have a sigma 2 formula, right? So a formula phi of x exists y psi, where psi is pi 1. Okay, then what can you do? Well, you can form the set of all pairs xy so that not psi holds of xy, right? That's a sigma 1 definable set. And now you can use this set x as a parameter to define the set of all x so that there exists a y, xy is not an x. Right? And that is the set you want. That's exactly the set defined by phi. So and then you can inductively, but in the real world, inductively, right, do this for 2, 3, 4, 5, etc. Right? For the actual numbers 2, 3, 4, 5. Okay. Also, you can, it's a nice exercise where you can prove induction for all arithmetical formulas. So you don't just have sigma 1 induction, you have full arithmetical induction. And then here's a result we're going to use a lot. This is a well-known standard result, right? But it's worth sort of going over. So ACA not proves that if you give me a function from the natural numbers to natural numbers, again, remember in RCA not we can code pairs, right? Therefore we can say what it means to be a function and so on, for a set to be a function. So if you have a function from the natural to number, then the range exists. And the range, of course, computability, if f is a computable function, the range is sigma 1 definable, so we would expect it to exist, and in fact ACA not proves it, right? So how do we get the range from ACA not? That's easy. It's a sigma 1 definable object. How do we go the other way? So suppose we have this formula phi of x as exists y psi xy, and now psi is, bounded quantifier. Okay, if C doesn't hold of anything, then there's not much to prove as far as defining the set. Right? So suppose it x0, and what we're going to do is basically we're going to monitor witnesses to this formula for different x's, right? So each time we have, we're going to set f of xy equal to x if y is the witness for phi holding of x. Does that make sense? And otherwise, we're going to define this to be x0. Right? Now we have exactly that the range of f is the set of x's. F is delta 1 definable. This proof is happening in RCA not, right? This f doesn't have any quantifiers in the definition. I guess the bounded quantifiers from C. All right, so that's a good, important baby result, right? That we are going to use a lot. Okay. Last thing maybe is, by way of introduction, I'll talk a little bit about semantics here. So what are models in this context? So we have L2 structures. Of course, L2 structure is an L2 structure. We know what the language is, so we know what a structure is. But we can take some small conventions here. So for example, in any such structure, we're going to interpret this first order equality. We can interpret it as actual equality. And this epsilon we can always just interpret as actual set membership, right? So we can do that. Really, right, what we're looking at is if you like, a model of PA, which may be non-standard, together with a collection of subsets of the universe of that model, right? With the actual set membership relation between the elements of the universe and the sets. Okay, the standard models, when that model of PA is standard, we call those omega models. I'm going to do a little bit more. I'm going to say that an omega model also has to have a condition on this set of subsets, which is that the collection of subsets is a Turing ideal. So it's going to be closed under Turing reducibility and joint. So if I have a set in there, anything it computes I also have in there. I have two sets in there, I have their join, right? Their effective disjoint union. Okay, so what can we say about the omega models of the two subsystems I mentioned? So the omega models, every omega model satisfies RCA naught. And the omega models satisfying AC naught are exactly what are known as the jump ideal. So they have to be closed under the jump, right? So if X is in there, X jump is in there. Okay? All right. Any questions? Okay, so let's go back to Ginsburg Sands. Now that we know how to do some reverse math, now we can say, okay, we have Ginsburg Sands theorem, we have reverse math. Let's do reverse math of Ginsburg Sands theorem. Right? A very nice way to formalize topological spaces, there are many, right? Or there are different applications for different sort of things. The one that we're going to focus on is this one due to Dore, which is for, right, it's a very natural setting, which is that, remember that in second order arithmetic we have numbers and we have sets of numbers, so in some sense we are very much confined or constrained by the need to be countable in some way, have some kind of countable representation, right? So we might as well look at countable topological spaces and topological spaces which have a countable basis, right? So countable second countable spaces. Okay, so as a CSC with capital letters isn't meant. I'm not defining what a countable second countable space is. I'm defining a formalization of a countable second countable space. So a CSC space is a tuple XUK. So X is an infinite set, and that will almost always just be N because why not? U now is a coded sequence of subsets of X. Just for simplicity, we can assume X is in here and the empty set is in there. Okay. So what is that representing? It's representing a countable basis. That's doing. And then this K function, okay, so a countable basis, a basis should be closed under intersection. This is essentially a way to kind of say, well, okay, if you have one basic open set, another basic open set, you should know what the intersection of those two basic open sets is, which means, if I have an index of one basic open set and an index of another basic open set, I should know an index of their intersection. So this is a kind of way to get at that, right? So what this says more precisely is, so it's a function that takes as input an element of the space and a pair of indices, and it outputs an index. And what this property is that if x is in the intersection of un and um, then x is in u sub k of x and m, and that is contained in the intersection of these. Okay, so that's it's a sort of convenient definition to work with. Okay, so that gives us a way to talk about countable second countable spaces in reverse math. And what else can we say? Open sets are more complicated. Open sets are unions of basic open sets, right? So in general, we're not going to have them kind of as realized objects, but rather we can talk about them in terms of codes, right? So we have an open code, which is just a set of indices, and that's coding the open set given by the union of the basic open sets with the indices in that set. That's the only time I'll talk about open sets in this talk, in this tutorial. So we're always going to talk about basic open sets. Anton. Right. It's a good question. I mean, so one is that it allows you to build things more, right? Because if you're, say, building open sets and you're wanting the basis to be computable, right? Then, for example, you might want at some point to enumerate something large into one of these basic open sets at a later stage or something like that. This gives you a little bit more flexibility that you don't have to have it exactly on the thing. I suspect for almost everything that would be the same thing for many, many applications. But I think this is just a little bit more flexible. Okay, so open sets are given like this. And then what's a subspace of a CSE space? So it's just going to literally be when I say a subspace of an X like this, I mean, give me an infinite subset Y and restrict everything to that Y, right? Which is maybe not completely natural in that when I say a subspace of a topological space, generally we think of this a restriction of the topological space, of the topology of the open sets, rather than the basic open sets, right? We don't necessarily use the same basis in a subspace. But you can always do. I mean, if I tell you here's a basis for a topological space and here's a subspace, then you can take that basis as the basis for this one, right? So there's nothing really lost here. Okay. All right, so now we can get back to the Ginsburg Sands theorem. So what do we have here? So suppose now that we are talking about a CSE space, right? So we are now having this discussion in second order arithmetic, right? In RCA naught. What does it mean to be indiscrete? Okay, so it's kind of obvious. Indiscrete means that all these UNs, all the basic open sets, are either empty or X. It's discrete if for every X there is an N so that the singleton is a basic open set. Cofinite topology, again, sort of obvious, right? Every open set is either empty or it's cofinite. Every basic open set. Okay, so where it becomes interesting is with respect to the initial segment and the final segment topology. And here's the definition we'll use. We'll use the kind of the strongest on its face definition you can think of, right? So we're going to say initial segment topology. X has the initial segment topology if there actually is a homeomorphism, right? So we have a bijection H from the naturals to X so that each N is equal to the image of an initial segment in the natural numbers, right? 0 to N for some, or 0 to, I guess, 0 to H of J for some J. Or of course, it could be the full set. And similarly for the final segment topology, so we always have this witnessing homeomorphism for the actual segment. That's, sort of a worrisome definition when you first see it, because you're thinking, well, we're doing reverse mathematics, we want somehow to be parsimonious in our definitions, right? We don't want to put a lot of heavy objects. And here we are already putting in we're saying there exists a function which is, a sigma 1,1, predicate in the definition of what this means. So you might say, well, we should try to scale it back and come up with something arithmetical as simple as possible. That's kind of the motto, right? We want definitions to be as simple as possible. So you can give an arithmetical definition, which will exactly say the same thing. There's a way to arithmetically define what it means to have the initial segment topology. We don't need to use it because this is more convenient, and since we're only interested in these things for subspaces, right? We're trying to build subspaces with certain properties. It turns out that if you have something with satisfying the arithmetical definition, say, of the initial segment topology, you can, in RCA0, prove that it has a subspace with this property. Right? Similarly for the final segment topology. If you want to prove that, you know, a space with the arithmetical definition of the initial segment topology also has the initial segment topology in this set, that it itself has that same definition, that turns out to be equivalent to ACA0. So that's elevating things somewhat. But we are only interested up to passing to subspaces, so we can use these definitions interchangeably. Does that make sense? Right, that since we don't care about the objects themselves, we always can pass to a subspace and just take the more useful definition, which is easier to work with. Okay. Okay, so this is what these things will mean for us. And now, of course, we can state the Ginsburg Sands theorem, right? So this is the Ginsburg Sands theorem as a principle in the language of second-order arithmetic, right? So here's the statement in RCA0. Every infinite CSC space has an infinite subspace that is indiscrete, has the initial segment topology, has the final segment topology, is discrete, or has the cofinite topology. And the order of these things, right, is chosen in the order of the proof, right? That's the way in which we encountered them in the proof. That's why I present it this way. One kind of terminological thing that I'll do is here is that I'm going to refer to problems like this and many, many other kinds of principles that we'll discuss as problems rather than as theorems or as statements or something like that, right? So, you know, GS has this very typical form that many principles have, right? Which is that it says for every set X with some property, there is a set Y with some property with respect to X, right? And typically these properties are arithmetical. They don't necessarily have to be, but usually they are. And we think of these as problems in the sense that we're sort of saying, you know, it's the problem given X, find a Y, right? That's the problem. So we think of these X's, right? The X's satisfying phi as the instances of the problem. And then given an instance X, we think of the Y's that satisfy this psi as the solutions to that instance, right? So an instance of the Ginsburg Sands theorem is an infinite CSC space. A solution to that particular infinite CSC space is a subspace Y, a subset of the domain, which as you know is a subspace in the sense of the definition of subspace, you know, has one of these 5 properties. Any questions on anything? Okay, so the task for the tutorial is to understand this theorem, right, in the context of reverse mathematics. Now, I want to say that, right, I mean, I'm going to put up this slide because I like it. So this is the reverse math 2. This is the kind of pantheon of all the different kinds of principles, or many, it's all growing every day. But these principles like Ginsburg Sands, well, I haven't yet shown you that Ginsburg Sands is one of them, but like say Ramsey's theorem for pairs and many others, which sort of live below ACA0, above RCA0, and are not equivalent to either of them, and are also not equivalent to WKL0, right? So I omitted from my casual introduction of reverse mathematics any mention of the big 5 phenomenon or anything like that, largely because it's not going to figure in this talk, right? But the big 5 phenomenon says that, I guess here it would be something like the big 3 phenomenon in this slide, right? That everything is either equivalent to ACA0, provable in RCA0, or equivalent to WKL0, which I didn't define. One of these systems, of course, there's two more that figure importantly in this scheme. But as you can see, there's a large body of counterexamples to that phenomenon, and I like them, right? So that's why I'm interested in this. So somehow we'd like to understand, you know, I mean, ideally you want to find some structure here or something like that, or find out what's going on. But finding new principles there that occupy interesting new positions sheds light on what's going on, right? It gives you somehow, it lets you isolate maybe If they're very different principles, but they're somehow closely related, you might say, well, what do they have in common? And somehow that's what's explaining the particular position. And we'll see that's exactly what happens here with respect to some principles related to Ramsey's theorem. So we'll talk about those. Okay, and I have till 12:30? Okay, so let me then go on to talk about Ramsey's theorem. So this I call the most important theorem in combinatorics. It's going to be very important in this talk, right? So this is the conduit from topology to combinatorics, right? So now we're going to switch a little bit to combinatorics. So what's Ramsey's theorem? So okay, so suppose we have an infinite subset or a subset x of omega, subset x of omega, or it could be the natural numbers if we're defining this in RCA naught. This bracket x to the n just denotes the set of all subsets of size n, or if you like, increasing n tuples, or however you want to think of it. And then a k coloring of x to the n is just a map, right, that assigns to each one of these n tuples one of the colors 0 through k minus 1. And the set is homogeneous for this coloring, let's say with color I less than k, if, this should be this is a copy paste. If C is constant on all the n tuples from H. Sorry about that, right? So if whenever you give me a size n subset of H, the color of that subset is I. So assume this is a tuple and this says H to the n. Okay, so Ramsey's theorem. Ramsey's theorem says for every nk bigger than 1, every coloring of n tuples with k colors has an infinite homogeneous set. And if you take n equal 1 and k equal 2, right, then you have the pigeonhole principle that we saw earlier, right? That's just coloring singletons with red or blue. Right? All right, so when we formalize this in L2, in the language of second order theory, right, the full statement is RT, and then we can do some restrictions, right? So RTN will just say for every k, every coloring of omega to the n with k colors has an infinite homogeneous set. RT and k will, in fact, do it for just k colorings of n to the k. And there's an important difference there, of course, that if we quantify the k or we quantify the n, then potentially these can be non-standard, right? And we'll see an example of why that matters. Okay. So here's a nice upper bound. Maybe this will be last theorem we proved today. So for each fixed standard n and k, ACA naught proves RT and k, right? And how do we prove that? So this is really an old result of Jacques that predates reverse mathematics as we know it, and then formalized by Simpson, right? And how do we do this? We prove this by induction on n, right? And it's important to note that this induction, right, what is it saying? It's saying for every coloring of such, for every n and every coloring, blah, blah, blah. That's a pi 1, statement, right? So ACA naught, as strong as it is, cannot do an induction like that. But we're not proving it. The induction is not being carried out in ACA naught, right? The induction is external. We're doing that in the real world. We're just proving for each individual n that ACA naught proves RT and k. Does that make sense? Right. So this is an important distinction, right? Okay. So for n equal 1, we can prove it in ACA naught, and you can think why that's the case. So let's assume the result is true for some n bigger than or equal to 1. And we're going to argue in ACA naught. And we're going to fix this coloring now from n plus 1 tuples to k. Okay, so here's a claim. There's an infinite set and a coloring now of n tuples, so that if you give me any tuple in that set x, any n tuple, and any y bigger than x, so any larger y in x, the color is the same, right? So this C again is operating on n plus 1 tuples, and D is operating on F, right? So what we're saying is that if I take an n tuple in here, its color with any larger y under C is the same as what D assigns it just to that n tuple. Does that make sense? Right? So if you think about it with pairs, I think it's a little bit simpler, right? You have an infinite set, and you have a coloring of pairs. That's what we started with. And what we're saying is that we have an induced coloring on singletons that's telling you, okay, the color of this is red under the induced coloring. That means that under the original coloring, the color of this with all the larger numbers is red. Right? So we've sort of pruned to arrange things in this way. Does that make sense? Okay, so you can think about how to construct such a thing. It's not hard how to do it, right? But now you can apply, of course, this is an instance now of RTNK, which we already know ACA0 can prove by inductive hypothesis. You can apply RTNK to that, get an infinite homogeneous set, and then check that that's also homogeneous for the original coloring. Right? That's the inductive scheme. Now, it's worth doing this. I don't have sort of formal exercises in this tutorial, but I have sort of these kind of little asides. And it's worth thinking, if you've not seen that proof, not worked a proof like that, it's worth doing it kind of carefully and making sure how to do it. In particular, because right here we have a infinite set which is not the natural, it's not n, right? It's not all of n. But the statement of RTN was for every coloring on the n tuples from n, right? Not from an arbitrary subset. It's worth thinking a little bit about why we can sort of do it, or how this, rather, how you actually do this, right? It's sort of worth playing with that if you've never done it. Okay. Oh yes, so maybe I'll save this for, this is the proof of how we actually do it. I'm going to skip it because I want people to think about it instead a little bit. But it will be in the slides, so you can look at it tonight when I put it on the website. Okay. So the last thing then maybe I'll mention today is this. I want to introduce these two important combinatorial principles. Right? These are CAC and ADS. So CAC stands for chain anti-chain principle. ADS stands for ascending descending sequence principle. And what we have is that these are the actual combinatorial principles that we already saw figuring earlier in that proof of Ginsburg Sands theorem. Right? These are just their kind of explications as statements. So CAC says every partial order on N has an infinite chain or anti-chain. It's very easy to formalize. What do we mean by an ascending sequence, descending sequence in RCA0? We're just going to say, right, because we can't say of type omega star, at least not without a lot of complexity. So we're just going to say if the set of an ascending sequence for L, if the set of predecessors of each element in that set is finite, descending sequence if the set of successors of each element in that set is finite. Okay, so that's nice and arithmetical to say that. And ADS says every linear order L on N has an infinite ascending sequence or descending sequence. So we've seen Ramsey's theorem. We know how to prove RTNK for every N and K. It's we in fact proved it in our ACA0. It's not hard to show that RT22, even Ramsey's theorem for pairs in two colors, implies CAC, and that CAC implies ADS over RCA0. Right? So that's another nice exercise to go home today and maybe play around with and try to see how you actually do these implications. In particular, both of these principles are provable in ACA0. Right? So at this point, every principle we've actually understood or sort of analyzed is living in that zoo. Right? It's somewhere below that ACA0. Okay. So the idea now then for the next lecture, I think this might be a good place to stop, will be to see how these principles actually can be deployed in the proof of the Ginsburg Sands theorem that we showed. Can we actually see where they're used, how they're used, and then where do we need to depart from that original proof, right? Or do we need to, or something like that, right? That's kind of the idea. Okay, but I'll stop here for today then.